going to look now at a concept called orthogonal functions. In addition to being a complete set, this set of eigenfunctions here that we worked out also has a property that they are orthogonal to one another. Now, you've seen the concept of orthogonality probably in geometry, where it means that things are at right angles. And there's an analogous sense here in which this is true, but we'll come back to that somewhat later. Basically, the property of orthogonality applies if we have two non-zero functions. That means this function mustn't be 0 everywhere, and this function mustn't be 0 everywhere. And these two functions are defined from 0 to LZ. Then they're orthogonal if this integral, the complex conjugate of g of z times h of z, integrated from 0 to LZ, is 0. That's what we're going to define as the orthogonality of these two functions, for the case where they're defined from 0 to LZ. And we could do some work and prove that all of these sine functions, with n as an integer here, are orthogonal to one another. It would take a bit of algebra to do that with sines and so on in integrals, but we could eventually prove that. And that would be, we'd be proving that all of these integrals are 0 unless n and m are the same thing. That is, if we're working with two sine waves with different integers in here, they are always orthogonal to one another. But if they have the same integer, they're not orthogonal, as we'll prove. This mutual orthogonality of different functions in a set is another common property of the eigenfunctions that we are going to be finding as we look at various different physical problems. Now, orthogonality is made much easier to understand and prove for functions if we happen to be able to make use of parity. Functions with opposite parity, such as the first two eigenfunctions of the particle in a box, are always orthogonal. Whatever contribution we get to the integral from multiplying this by this and adding it up, and this by this and adding it up, and this by this and adding it up, is always cancelled out by the corresponding products, this times this plus this times this, and so on the right-hand side. Everything cancels out if we perform this integration here. These functions, as I've drawn them, happen to be real, so the complex conjugate is rather trivial. And the important point is, if we happen to have these parity relations, we can see the orthogonality of them without even having to work out any integral. So functions with opposite parity are always orthogonal to one another. With sine functions like this, even those sine functions, however, of the same parity are also orthogonal. That's not so obvious, but it is also true, and we said that was the case earlier on. For example, the n equals 3 eigenfunction here is orthogonal to the n equals 1 eigenfunction. You can't deduce that orthogonality from a parity argument, but nonetheless it is orthogonal. The positive chunks that we get from this region multiplying this function and this region multiplying this function just happen to be cancelled out exactly by the negative chunk we get from this region multiplying that function. Now, we can introduce a concept called orthonormality that is very convenient. And to do that, first of all, we introduce a notation called the Kronecker delta. So this says that this little object here for subscripts n and m is 0 unless n equals m, in which case it's 1. It's just a notation. It's a very convenient notation. So this little object is 1 when the two subscripts are the same, and it's 0 when the two subscripts are different. For our normalized eigenfunctions, therefore, we can write the orthogonality and the normalization as one condition if we put the Kronecker delta on the right. So the normalization, where n would be equal to m, this would be the normalization integral. If these are normalized functions, the answer on the right would be 1. If n is not equal to m, because these functions are orthogonal, the answer on the right will be 0. So we can write the orthogonality and the normalization condition in one expression. And a set of functions that is both normalized and mutually orthogonal is said to be orthonormal. It's just a shorthand way of stating both of those properties at once. And for a set of functions, this would be the orthonormality condition here.
Orthonormal sets are extremely convenient mathematically, so most basis sets are chosen to be orthonormal. Note again, incidentally, as we said, that orthogonality of different eigenfunctions is very common in quantum mechanics. And it's not restricted to this specific example where the eigenfunctions just happen to be sine waves. Orthonormal sets allow one particularly useful trick, which is to find the expansion coefficients. Those are the coefficients that tell us how to represent some function on our orthonormal basis.
Now we're going to return to solve a little problem that we had left hanging here. How do we figure out what these expansion coefficients are? In other words, suppose we wanted to write this function, f of x, in terms of a complete set of orthonormal functions, these psi n of x. That is, we want to write out this summation. How do we figure out what these little coefficients actually are in this expansion here? So to find these expansion coefficients, Cn, it's actually quite simple. We pre-multiply both sides by psi m star of x, and we integrate. Let's see that at work. We pre-multiply by psi m star of x and integrate, and that gives us, on the left, this integral here. And on the right, therefore, what we're looking at is, here we've substituted for f of x with the expansion. Then we flip round the order of the integrals and the summations, which works for the kinds of functions we're looking at here. So now we've got a sum over n of Cn times these integrals. But these integrals here, because this is an orthonormal set, are just the Kronecker delta. That is, they are 1 if m is equal to n, and they're 0 otherwise. And that means that this whole summation collapses. The only term that remains in this summation is the one for m equal to n. And so finally, we have our coefficient. If we have a complete orthonormal set, we can now expand any function in it. Incidentally, an integral like this is generally called an overlap integral, and that's a concept that will come back again and again.